Hello, 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 and welcome to Shake the Costa. Today we're going to learn about properties of exponential functions. Today we're going to learn about something called the exponential function, and that is f of x equals a times b to the power of x. And this is one of the most important functions you'll end up learning in your life. And as part of this lesson, you should be able to, by the end, graph, with or without technology, an exponential relation if you're given its equation or any other information about it. You're going to define this relation as a exponential function, and you're going to be able to explain why it's a function. And you're also going to be able to determine the key properties, including domain and range, the intercepts, whenever it increases or decreases, and a new word called an asymptote. To start off, you can do this experiment either standing away from a wall, or you can simulate it using a coin and a desk and a ruler. All you have to do is stand 8 feet from the wall, or put the coin 8 centimeters or whatever from the edge of the ruler, and then start taking steps towards the wall, or moving the coin towards the end of the ruler. And every time you take a step, we're going to hear the number of steps. You're going to measure how far you are from the wall, and you must cover half the remaining distance between you and the wall. And you can record that data on the table. And once you're done, so pause the video, go ahead and do that. And once you're done, we'll take this up. Well, as I do this, and I'm going to do this using a simulation using a coin here, this coin starts here exactly 8 centimeters away from the edge. After one step, I'm going to move it all the way over to here so that half of 8, that's 4 centimeters are remaining. If I take another step, again, half of 4 now is 2. So I've covered 2 centimeters, and now there are only 2 centimeters remaining. Or if you were taking steps towards the wall, 2 feet. Another step takes me to 1 centimeter remaining. Another step takes me to half a centimeter remaining. Another one will take me to, it's getting pretty hard here, 0.25 centimeters. And then another step, that's even harder to measure, but it looks like it's just past the 1 notch there, 0.125 centimeters. And if you notice, to be able to, the pattern that this follows is we always seem to be dividing the remaining distance by 2. So from 8, we divided that by 2 to get to 4. And another way to say divide by 2 is, of course, multiply by a half. And the reason I'm going to change it from division to multiplication is because we're learning about exponential functions. And that happens when we repeatedly multiply by the same number. And every single time here, we're multiplying by 1 over 2 to get our next distance. The question is, how long would it take you to reach the end of the wall? Would you be able to do that after 50 steps? Doesn't seem like there's a lot of space remaining. Let's take a look. So what would the distance be between you and the wall after 50 steps? And what would the distance be after an unknown number of steps? And I've added those 2 lines to the table here. And to do this, instead of measuring, you could see it was even really tough to measure after 6 steps. So instead of measuring, we're going to have to calculate the distance. And you can see that this is sort of the path our steps took. This is the distance remaining to the wall after so many steps. When we took 0 steps, we started at 8 feet from the wall. And then after 1 step, it was down to 4. After another step, it was down to half of 4, which is 2. And we kept on going from there. So we started here. That was 8. And how did we calculate this number here, 4? Well, we took 8 and we multiplied it by a half. How did we get the next point? Well, we took whatever number that was, 8 times a half, which we know is 4, but I'm just going to leave it as 8 times a half, and we multiplied by a half again. So 8 times a half, and then times another half. Again, to move to the next step, we took this and multiplied it by a half again. So you notice that we are repeatedly multiplying by the same number. And when we do that, we can actually take this, and another way to express it is we did 8 times a half 3 times to the power of 3. Well, following that logic, multiplying it by a half one more time would make this number go up. So over here, we're at 8 times a half to the power of 4, 8 times a half to the power of 5, 8 times a half to the power of 6. And if I wanted to find out how far we would be after 50 steps, notice that the powers, the exponents, are the same as the number of steps. So all I have to do is find out 8 times a half to the power of 50. And when I do that, I get a really, really long number. In fact, 0 point, and there's a bunch of zeros that I'm skipping here. And another way to express that would be using scientific notation. So 7.11 times 10 to the power of negative 15. And what that means is you can take the decimal and move it to the left 15 spaces. So there's 15 zeros before the 7. Whoa, that's a really, really small number, but it's not quite 0. We haven't reached the wall yet. Even though it's a tiniest fraction of a centimeter from the wall, or an inch or feet or whatever you want to measure it from the wall, we haven't reached it yet. And to find our distance after x steps, clearly, like we just were able to do that here, we can do 8 times 1/2 to the power of x. This is an exponential function. An exponential function is defined as f of x equals a times b to the power of x. The independent variable in an exponential function, this is why we call it an exponential function, is because the independent variable is in the exponent. The initial value, or the starting point, or the y-intercept, is easily found by just a, whatever that a value is. Okay, that number that is in front of this multiplication of the power. And we call the number that we're actually multiplying either the growth factor, if it's more than 1, or the decay factor, if it's less than 1. And we can see that the reason we call it the decay factor is because our values are decaying. They're going down, they're decreasing as the number of steps, or as the independent variable increases. So when will we know that after 50 steps, we will be this many feet away from the wall. When will we actually reach the wall? The simple answer is never. This behavior of getting closer and closer to a number without never actually reaching it is called asymptotic behavior. That's a tough word to pronounce, so I'll give you a chance if you want to pause the video here and try to give that a shot. This line down here is the equation, this line which has the equation y equals 0, is called an asymptote. And you can see what these two words are related, right? What is an asymptote? Well, it's an imaginary line or a value that the graph of a function gets closer to without ever reaching it. So it approaches it, but it will never actually get there. The distance between the points and the line keep getting smaller, but because they're getting smaller multiplicatively, they will never actually reach 0. This is called asymptotic behavior. And as part of this, we're going to explore this idea quite a bit. So I'd like you to pause the video here and copy this table down. And for each equation here, I've given you the value of A and the value of B and the equation itself. You can graph it using graphing technology. And if you'd like to use Desmos, here is a QR code, which you can go ahead and scan. And change the A and B values, sketch a quick graph, a very rough graph in each of these spaces, and then try to find out what is the domain range, the asymptote, any intercepts, and when the function is increasing or decreasing. And when you're done, you can resume the video, and I'll take these up one at a time. Okay, so for our first graph here, this is what f of x equals 1 times 2 to the power of x, which is just the same thing as just 2 to the power of x. I don't really need this 1 times, right? This is what it looks like. And the domain, we can clearly see, is any real number. Notice that there's no limit on what number we can put in for x. We can even put in negative numbers, and the function still exists. It passes the vertical line test. The range, I'm not going to write out the full version of the range here, but the range seems like this function, it seems like it exists above the x-axis only. It's asymptotic as it gets more to the left, so it's going to get closer and closer, but it'll never actually touch the x-axis. And on the right side, it seems like it's increasing. And so I would say the range of this function is f of x has to be greater than 0, not equal to. And the asymptote here is y equals 0. That is the equation of a line. That's the x-axis right there, where the function is getting closer to, but it will never actually reach. Because it never reaches the x-axis, there actually is no x-intercept. But it does have a y-intercept, and that y-intercept is right here at 0, 1. When is this function increasing? Basically all the time, and it's never decreasing. Once we increase the growth factor from 2 to 3, notice what happens. Ooh, the function is actually increasing, maybe a little bit faster. Its domain is still any real number, and it still only exists above 0, and the asymptote is still y equals 0, and it still doesn't have an x-intercept. Its y-intercept hasn't changed either. Isn't that interesting? Even though it looks like it's rising faster, the y-intercept is still 0 and 1. And it's always increasing and never decreasing. So notice how many similarities there are when we increase the growth factor b. Let's see what happens when we increase the initial value from 1 to 2. Well, it looks like the function is still increasing faster, but the domain and the range and the asymptote have not changed. There's still no x-intercept, but now the y-intercept has changed. Now it's at 0 and 2. It's still always increasing and never decreasing. Well, what if we stop increasing the growth factor? What if we decrease it instead to 0.5? Well, now that has created quite a different graph. There's still a lot of similarities. For example, the domain, the range, the asymptote. There's still no x-intercept. The y-intercept actually is still the same as it was before, 0 and 2. And now, though, instead of always increasing, it's never increasing, and it's always decreasing. The function is always going down. If we mix things up just a little bit more, if we change that initial value to being a negative number, notice that this graph is exactly the same as this, except it flipped upside down. And so the domain hasn't changed, but the range has. Now, instead of always being above 0, the function is always less than 0. It's always underneath that x-axis. The asymptote is still y equals 0. Notice that the function is getting closer and closer to the x-axis still, but never actually going to touch it. There's still no x-intercept, and the y-intercept now is actually 0 and -2. So now it's, because it's upside down, it used to be a +2, now it's at -2. And now it went right back to increasing and never decreasing. These last two experiments that I've asked you to change it to ask the question, well, what if we make this first number 0? What does that do? And it looks like that just makes a perfectly horizontal line. Its domain hasn't changed, but the range is just a single number. It's always, the y values are always just 0. There is no asymptote, and the x-intercept is, well, it's always touching the x-axis. So, we could say there's an infinite number of x-intercepts, and it intercepts the y-axis at the origin 0, 0. This function never increases, and it also never decreases. If we go back and change this back from being 0 all the way back to being 1, but now we change the growth factor to 1, notice that you get a very similar graph. And I'll explain why that is in just a minute when I do some comparisons, but the domain is still any real number. The range now is just 1. All of the y values are equal to 1. It's a horizontal line, but it's slightly higher than this one. There is no asymptote, and there is no x-intercept, and the y-intercept is 0 and 1. It also never increases, and it never decreases. Let's take a look at what happened when we changed from this graph to this one. So we increased the growth factor from 2 to 3, and we notice that the graph does rise faster. But when we look at all of these characteristics, none of them actually changed, right? So we can say that increasing the growth factor doesn't always do anything. Like, it certainly makes the graph rise a little bit faster, but it doesn't change any of these properties. When we increase the initial value from 1 to 2, that changed some things. Well, that made the graph rise even faster than it did before, but many of the properties still remain the same. The domain, the range, the asymptote, the x-intercept. But something did change, and it did change in a very unique, very special way. The y-intercept changed from 0, 1 to 0, 2. The increasing and decreasing intervals didn't. So I'm going to focus on just this one. Why did that change to 0, 2? Well, if I plug in the x value 0 into either of these equations, 3 to the power of 0, or even 2 to the power of 0, anything to the power of 0 is equal to 1. And so this would be 1 times 1, which is how we get 1. This would be 1 times 1, which is how we get 1. This would be 2 times 1, and that's how we got 2. So it looks like because this power will always equal 1 when x is 0, the y-intercept seems to be reliant entirely on this one right here. And in fact, we can confirm that, for our second graph and for our third graph, the y-intercept exactly matched the a value. If we look back to the first graph, we see that's true there too. And even if we look forward to our other graphs, yep, that's the y-intercept and that's the a value. Same with this graph over here, the fifth one. And even as we go into the other non-exponential looking functions, the ones that looked very different, we would see that that is still true in this case. So that makes sense. The a value in f of x equals a times b to the power of x. That tells you exactly what the y-intercept is. And that, of course, makes sense. The y-intercept always happens when x is 0, and f at 0 will always turn the power into 1. And then we'll just be multiplying 1 times a, which is just a. From our third to our fourth graph, we decreased the growth factor to a number that's less than 1, a number like 0.5, and we saw that the graph switched from going up to going down. The domain, the range, the asymptotes, the x-intercepts, even the y-intercept did not change because we did not change the a value. But the increasing and decreasing intervals did switch, right? They changed vice versa. And so now the function is always decreasing and always increasing. And so when the growth factor b is less than 1, what does that mean? That means that whenever x increases, we're multiplying by a small number, a number that's smaller than 1. And whenever you multiply a number by a number that's smaller than 1, it decreases your value. And therefore, as x increases, the y values are continually decreasing because they're getting half as big each time. From there, we flip this graph upside down. We changed the a value to negative, although we kept the growth factor the same, and that made the graph upside down. The domain didn't change, but the range did. And that's, of course, obvious because it reflected across the x-axis. And if you're familiar with transformations of functions, then you know that that's exactly what the a value does. The number in front that's being multiplied by a function, if it's ever negative, it flips the function upside down. Most of the other things didn't change, except, of course, we recognize this already, the y-intercept did. And the increasing and decreasing intervals did switch. And that's because, if it's upside down, whatever was increasing before would now be decreasing, but the whole function was decreasing before, and now it is never decreasing, always increasing. So when the b value is less than 1, we started off with decreasing. But now that we have made the a value negative, that has changed, that has flipped that back around. Taking a look at these last two functions at the same time, how come they created flat lines? Aren't we still in this sort of exponential structure? Well, for this one, f of x is always going to equal 0, or the y value will always be 0, and that's because no matter what this value is, we're always going to multiply it by 0, and that anything multiplied by 0 is 0. So that's what makes this a linear relation, and definitely not exponential. Over here, when the base was 1, well, no matter what we change x to, 1 to the power of anything, 1 multiplied by itself any number of times is always going to be 1. And therefore, this is always going to be 1 times 1. And that is exactly why all the y values are 1. So that is a linear relation. It's a straight line, and it's not exponential. And so the real takeaway here from these two, is that in order for this to be an exponential function, b must be greater than 0, can't be equal to 0, and it definitely can't be less because that creates all sorts of other problems that we did not explore here. And it can't be equal to 1 because that also makes the function a straight line. And finally, the a value also cannot be 0 because that would negate anything you're trying to do with this power over here. This is the definition of an equation of an exponential function. Of course, there are some restrictions, like b has to be greater than 0, it can't be 1, and a can't be 0 either. But as long as you abide by these restrictions, this will create a graph that is either decaying or growing exponentially. Okay. It decays if the growth factor, if the B value is between 0 and 1. But if it's more than 1, then the function will grow. And this is both this arrow, the fact that this is arrow means an arrow is has two meanings. It means that, of course, all the numbers greater than 3 mean that it is still a growth exponential function, but it's also pointing to the actual example of one. An exponential function always has an asymptote at y equals 0, and its y-intercept is always 0, comma, whatever the a value is. The graph looks exactly like you see over here. So one end is really, really flat because as it approaches the asymptote, it gets closer and closer to it. And the other end rises really, really sharply, really quickly. And even more so when you increase the growth factor here. The domain of any exponential function is any real number because, of course, you can take whatever number that's in the base, you can multiply it by itself any number of times, even a rational number of times. And the range of this function is any value as long as it's greater than 0. But this only applies, of course, if a is positive. If a is negative, you need to flip this sign. So this implies that f of x will never actually be 0 because it's not greater equals, it's just greater. And so therefore there is no x-intercept for exponential functions. In this example, we're going to determine the intercepts domain range and the equation of any asymptotes that appear for this function right here. And this is an exponential function because the independent variable n is in the exponent. Once we're done that, we're going to sketch out a graph very roughly. So always any exponential functions have no x-intercept, and the y-intercept is always 0 and the a value, which in this case is not a rational number, it's pi. And that's okay, pi is still a number, so I'm just going to label the y-intercept as 0, pi. The domain of this is like any exponential function, any real number, so n can be any real number. And the range is g of n such that it is greater than 0, but it can be any real number greater than 0, including irrational numbers like we see here. Every exponential function has an asymptote at y equals 0. And when we look at the growth factor, it's actually a decaying factor because it's less than 1. Right? 9 over 10 is like 0.9, and that's a number that's smaller than 1. So the function will be decaying. In other words, it'll be decreasing. And if I wanted to sketch that as a graph, I'll just have to plot the y-intercept first, which pi is about 3.14, so I could put a dot just about over there. And then I just need to make sure that it's decaying, and I'll sketch the graph so that it approaches the asymptote, which is y equals 0, right over there, but it never actually touches it. So sort of like this, right? That's my rough sketch of this function. If you like this video, please like, rate, subscribe, and join our mailing list. And you can find this lesson as well as practice questions, solutions, handouts, and more on our storefront. Thanks and have a great day.